In practice, contractors often prefer to ground separately derived systems at the first means of disconnect. This approach is generally viewed as more convenient and cost-effective. Grounding at the first means of disconnect provides several advantages. Firstly, it allows for all grounding connections to be made at one accessible location, simplifying inspection and maintenance. Secondly, it tends to be more cost-effective because the main bonding jumper does not need to be oversized, reducing material and labor expenses. Thirdly, space saving is realized as there is often limited space within the transformer enclosure to accommodate additional connections. One potential disadvantage of grounding at the first means of disconnect is the possibility of a voltage drop between the neutral and ground conductors if the load imbalance and distance are significant. However, this is generally not a major concern in most applications. Grounding separately derived systems at the transformer enclosure is less common. It might be employed in specific scenarios, such as when the neutral and ground conductors are already bonded within the transformer enclosure, when the distance between the transformer and the first means of disconnect is very short, or when a custom transformer with specific grounding arrangements is required. Grounding at the transformer enclosure offers the advantage of equipotential grounding. Bonding the neutral and ground at the transformer ensures they are at the same potential, eliminating any potential voltage difference. However, this method also has disadvantages. Firstly, the main bonding jumper must be oversized per National Electrical Code Section 250.66, increasing material and labor costs. Secondly, as previously mentioned, there may not be enough space within the transformer enclosure to accommodate all the necessary connections. In conclusion, while both methods are acceptable according to National Electrical Code Article 250, grounding separately derived systems at the first means of disconnect is generally preferred by contractors due to its convenience, cost-effectiveness, and ease of maintenance. Grounding at the transformer enclosure may be used in specific scenarios where the advantages outweigh the disadvantages. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including the grounding of separately derived systems. Article 250 within the NEC specifically addresses grounding and bonding requirements. A separately derived system is an electrical power source such as a transformer or generator that is not directly connected to the main service entrance. Grounding these systems is crucial for safety and proper operation. There are two primary methods for grounding a separately derived system: 1 at the transformer enclosure, and 2 at the first means of disconnect. The first means of disconnect is the first overcurrent protective device, such as a circuit breaker or fuse, located after the separately derived system. When grounding at the transformer enclosure, the neutral and ground conductors are bonded together within the transformer enclosure itself. This creates a direct connection between the neutral and ground, ensuring that they are at the same potential. The main bonding jumper, which connects the equipment grounding conductor to the grounded conductor, must be sized according to National Electrical Code Section 250.66. Due to concerns about harmonic currents, some specifications require 200% neutrals, which means the neutral conductor is twice the size of the phase conductors. This can further increase the size of the main bonding jumper and the required conduit size. One advantage of grounding at the transformer enclosure is that it ensures equipotential grounding, meaning the neutral and ground are at the same potential, minimizing voltage differences. However, this method can be more costly due to the oversized main bonding jumper and the increased conduit size. There may also be limited space within the transformer enclosure to accommodate all the necessary connections. When grounding at the first means of disconnect, the neutral and ground conductors are bonded together at the first overcurrent protective device after the transformer. This method is generally preferred by contractors due to its convenience and cost-effectiveness. It allows for all grounding connections to be made at one accessible location, simplifying inspection and maintenance. Since the main bonding jumper does not need to be oversized, the cost of materials and labor is reduced. One potential disadvantage of grounding at the first means of disconnect is the possibility of a voltage drop between the neutral and ground conductors. This can occur if the load imbalance and distance are significant. However, this is typically not a major concern in most applications. Factors to consider when choosing a grounding method include cost, convenience, space constraints, and the potential for voltage drop. Grounding at the first means of disconnect is generally the preferred method for its convenience and cost effectiveness. However, grounding at the transformer enclosure may be necessary in specific scenarios, such as when the neutral and ground conductors are already bonded within the transformer enclosure, or when a custom transformer with specific grounding arrangements is required. Ultimately, the choice of grounding method should be based on a thorough evaluation of the specific application and the requirements of the National Electrical Code. Remember to consult with a qualified electrical engineer or contractor to ensure that the grounding system is properly designed and installed. Sizing the main bonding jumper correctly is essential for safety and code compliance. National Electrical Code Section 250.66 provides guidelines for sizing the main bonding jumper based on the size of the service entrance conductors. An oversized main bonding jumper may be required in certain situations, such as when the neutral conductor is oversized or when there are concerns about harmonic currents. Ensuring that there is enough space within the transformer enclosure for all the necessary connections is also important. If space is limited, it may be necessary to use a larger transformer enclosure or to ground at the first means of disconnect. Voltage drop between the neutral and ground conductors can be minimized by using appropriately sized conductors and by keeping the distance between the transformer and the first means of disconnect as short as possible. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes checking the tightness of connections, inspecting conductors for damage, and testing the grounding impedance. By following these guidelines, you can ensure that your separately derived system is properly grounded and that your electrical system is safe and reliable. The primary difference between grounding at the transformer and grounding at the first means of disconnect lies in whether neutral and ground conductors are bonded together. At the transformer, this bonding occurs within the transformer enclosure, while at the first means of disconnect, it occurs at the first overcurrent protective device after the transformer. Each method has its own set of advantages and disadvantages. Grounding at the transformer ensures equipotential grounding, but it can be more costly and require more space. Grounding at the first means of disconnect is generally more convenient and cost-effective, but it may result in a voltage drop between the neutral and ground conductors. The choice of grounding method should be based on a careful evaluation of the specific application and the requirements of the National Electrical Code. Consulting with a qualified electrical engineer or contractor is recommended to ensure that the grounding system is properly designed and installed. When selecting a grounding method, it is important to consider the potential impact of harmonic currents. Harmonic currents are non-sinusoidal currents that can cause overheating and other problems in electrical systems. An oversized neutral conductor and main bonding jumper may be required to mitigate the effects of harmonic currents. It is also important to consider the potential for voltage drop between the neutral and ground conductors. Voltage drop can be minimized by using appropriately sized conductors and by keeping the distance between the transformer and the first means of disconnect as short as possible. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes checking the tightness of connections, inspecting conductors for damage, and testing the grounding impedance. By following these guidelines, you can ensure that your separately derived system is properly grounded and that your electrical system is safe and reliable. The location of the neutral ground bond in a separately derived system significantly impacts the flow of fault current and the overall safety of the electrical system. When the neutral and ground are bonded to the transformer, any fault current will have a direct path back to the source, resulting in a faster and more reliable operation of overcurrent protective devices. This can help to minimize the risk of electrical shock and fire. However, bonding at the transformer also means that any neutral current, including harmonic currents, will flow through the equipment grounding conductors. This can cause nuisance tripping of ground fault circuit interrupters and other problems. When the neutral and ground are bonded at the first means of disconnect, the fault current path is less direct, but it still provides adequate protection. This method also minimizes the flow of neutral current through the equipment grounding conductors, reducing the risk of nuisance tripping. However, it is important to ensure that the distance between the transformer and the first means of disconnect is not too long, as this can increase the impedance of the fault current path and slow down the operation of overcurrent protective devices. The National Electrical Code provides specific requirements for the size and installation of grounding conductors and bonding jumpers. These requirements are designed to ensure that the grounding system can safely carry fault current and provide adequate protection against electrical shock and fire. It is essential to follow these requirements carefully when designing and installing a separately derived system. In addition to the location of the neutral ground bond, the type of grounding electrode used can also impact the performance of the grounding system. The NEC recognizes several types of grounding electrodes, including ground rods, ground plates, and metal underground water pipes. The choice of grounding electrode will depend on the soil conditions and other factors. It is important to select a grounding electrode that provides a low impedance path to ground. Regular testing of the grounding system is essential to ensure that it is functioning properly. Grounding impedance testers can be used to measure the impedance of the grounding system and identify any problems. Any problems with the grounding system should be corrected immediately to ensure the safety of the electrical system. Separately derived systems are commonly used in commercial and industrial buildings to provide power to sensitive electronic equipment and other loads. These systems are often used to isolate critical loads from the main electrical system, providing a high level of reliability and protection. However, it is important to ensure that separately derived systems are properly grounded to prevent electrical shock and fire. Grounding is a critical aspect of electrical safety and should never be overlooked. By following the requirements of the NEC and consulting with a qualified electrical professional, you can ensure that your separately derived system is properly grounded and that your electrical system is safe and reliable. Ultimately, understanding the nuances of grounding separately derived systems, whether at the transformer or the first means of disconnect, requires a comprehensive grasp of the National Electrical Code, practical experience, and a commitment to safety. This ensures electrical systems operate reliably and protect people and property.